Hello, class. In this chapter, we're going to begin learning about electric current. Current is a flow of electrons. In previous chapter, we discussed about electrostatics, which is electrons moving from point A to point B. In this chapter, electrons are continuously flowing. Mathematically, current is defined as a rate of charge through a conductor. I is a variable we'll use for current. You already know Q stands for charge and T stands for time. Instead of writing coulombs per second for the unit of current, we'll use capital A, which is named after Mr. Ampere. A complete circuit is one where current, which is electrons, can flow all the way around in a closed loop. In order for current to flow, there must be a path from one battery's terminal, say the positive end, through the circuit and back to the other battery's terminal, which would be the negative end. Only one of these circuits will work. Can you guess which one? Correct, C. The last diagram is the only one that shows current flowing through a closed loop, including both terminal ends of the battery. By convention, current is defined as flowing from positive to negative. Electrons, though, actually flow in the opposite direction. So think of all circuit diagrams we'll deal with current flowing from positive to negative, but just technically know it's the other way around. Alright, I think we're ready for our first example. A steady current of 2.5 amps exists in a wire for 4 minutes. How much total charge passes by a given point in the circuit during those 4 minutes? We'll start with our new equation, but first we need to convert minutes into seconds to get 240 seconds. Now we can rearrange the equation to solve for charge. From there, it's a straight plug and chug to get 600 coulombs passing through the wire. To calculate the number of electrons, we need to know the charge of one electron is 1.6 times 10 to the negative 19 coulombs. So with 600 coulombs divided by 1.6 times 10 to the negative 19 coulombs to find out how many electrons are in 600 coulombs. And we get 3.8 times 10 to the 21 electrons. Now, we're going to learn a very important law that we'll use very frequently, and that's Ohm's law. Experimentally, it is found that current in a wire is proportional to the potential difference between its ends. The equation you should box in your notes is V equals IR, where V stands for voltage, or potential difference, I stands for current, and the new variable R stands for resistance. An analogy for resistance is to think about boulders in a river. Boulders disrupt and resist the flow of the river. The boulders would be the resistance, and the water flowing would be like the current. The more resistance, the more obstacles the current or electrons have to go around. In many conductors, the resistance is independent of the voltage. This relationship is called Ohm's law. And the unit for resistance is a Greek symbol omega, called ohms. A cartoon diagram of what a resistor component looks like is in the figure to your left. The different colors are codes that are letting you know how high or how low the resistance is in that component. The figure to your right shows a mixture of resistors and other circuit components. Okay, I think we're ready for our first example. A small flashlight bulb draws 300 milliamps from its 1.5 volt battery. What is the resistance of the bulb? First, let's start off with Ohm's law, V equals IR. Rearrange the equation to solve for resistance. And plug and chug to get 5 ohms of resistance in the light bulb. Notice how I changed milliamps to amps for current, And the last thing to note is that light bulbs act like resistors. For part B, if the battery becomes weak and the voltage drops to 1.2 volts, how would the current change? Well, now we know the resistance of this light bulb is 5 ohms. We'll use our Ohm's law equation again, rearrange to solve for current, and then plug in our new value for voltage to get a current drop of 0.24 amps, or I can say 240 milliamps. So less current is drawn out from the battery as its voltage drops over time. Now let's say current enters a resistor R as shown below. Is the potential higher at point A or point B? Point A is at a higher potential than point B because the current label flows from positive to negative. As the current flows through a resistor, the potential decreases and is often called a potential drop or a voltage drop. Now current I enters through a resistor as shown below. Is the current greater at point A or at point B? The current is the same at point A and point B. Current does not get used up by the resistor. The resistance of a wire is directly proportional to its length and inversely proportional to its cross-sectional area. Now every wire is made differently and will have a different resistance, which affects the flow of the current. You can calculate this resistance in a wire with this equation. The Greek letter rho is called resistivity, and it depends on the type of material the wire is made out of. L stands for the length of the wire, and A is the cross-sectional area, which is the thickness of the wire, where we'll assume all wires have a circular cross-sectional area. Here's a table showing different constant values of resistivity. Copper is probably most commonly used, but silver has a slightly lower resistivity. And obviously rubber has a very high resistivity and does not allow electrons to flow very easily at all. Alright, let's do an example. So suppose you want to connect your stereo to remote speakers as shown below. If each wire must be 20 meters long, what diameter copper wire should you use to keep the resistance less than 0.1 ohms per wire? Let's start with our new equation. Rearrange the equation to solve for area or cross-section because we want to find the diameter of the wire. From the resistivity table, I found that the constant value for copper, and then I plugged in chug to get 3.4 times 10 to the negative 6 meters. With the value of area, we can use the area of a circle, pi r squared, but first we need to solve for the radius. We can plug in chug to get 1.04 times 10 to the negative 3 meters. And lastly, multiply this number by 2 to obtain the diameter of the wire, which ends up to be around 2.1 millimeters. Now for part B, if the current to each speaker is 4 amps, what is the potential difference or voltage drop across each wire? We can use Ohm's law, V equals IR, plug and chug, and we get 0.4 volts. The last note I want to leave you with is that the higher the resistance is, the less current that is drawn from the power source. But the value of the current drawn will stay the same across the resistor.